University. Today I will talk about the mixing of the multiple wave documental view and the implications in the neutrino physics. This talk is based on our recent paper, and they was started in PRT 2 days ago. Thank you. And they collaborate this with somebody. There are many documenters models over the wide mass ranges. Already we've talked many models in this workshop, like as PBH, compass documenters, with underlying documenters. And today I'll focus on the ultralight documenters, which show that wave-like behavior. Such ultralight documenters mass can be motivated by to address the solitonic cosine of the Dwarf galaxy. If the wave documentor mass is around 10 to the minus 20 electron volt, represents a body documentor, that the wave length is correspond to the 1 kiloparsec, which is consistent with the solitonic density profiles of the Dwarf galaxy. And also the QCD action or ARP can provide the ultralight mass scale naturally. There are mass bounds around ultralight documenters. The lowest bounds confirms structures formation. The small scale structure, the surplus in the wave documenters, and the Lyman alpha Boris gives the low bounds as 10 to the minus 22 electron volt. And upper bounds coming from the requirement of the wave-like behavior. The de Broglie wavelength should be longer than the interparticle separation, or equivalently, the occupation number in the de Broglie wavelength value should be larger than the 1 to treat as a classical wave. And this gives the upper bounds as the sub-electron volt. There are many observational and experimental proofs of the ultralight wave documenters. Like I mentioned, the metaphor spectrum can be significantly different compared with the typical core documenters model. And also the wave documenters can provide the galactic structures with the solitonic density profile. This can be analyzed by the Schrödinger coupled system. And also the black hole can make the ultralight wave documenters cloud by the Schutter radiance, and this can prove some mass ranges of the wave documenters. And also the wave documenters can make the time-dependent perturbation over the space-time, and this can be provides the first timing elements or the asymmetric detection for the wave documenter task. In this talk, focus on the modulation signal, such as wave-like behaviors of the ultralight documenters. Such oscillating behavior can affect to the laboratory proof, like as the atomic clock or solid-state system or superconductor. The oscillating behaviors of the wave documenters can be analyzed with the varying action in the expanding universe and the equation of the motions are varying. When the Hubble friction time is large, the field value was frozen in the extraliminal universe. But when the Hubble terms are negligible compared to the wave document mass, it starts oscillation behavior. Such oscillating behavior can directly transfer to the other particle sectors via the interaction. There are a list of the possible interaction between the wave documenters and the other particle. So if the wave documenter coupled to the gauge boson, like as a photon or gluon, and fundamental quantities like as Weierstrass constant or QCD combined and scale can be modulated over the time. Or if the wave documents coupled to the baramium, then their masses also can oscillate over the time. So such a modulations of the fundamental quantity can make some temporal signal, and this can be tested by the atomic clock or the some precisions observable, or also the neutrino wave oscillation can be affected. So far I only focused on the single wave documenters, which provides the simple harmonic oscillations through behavior. But one can generalize these simple assumptions to the multiple wave documenter field and mixing between each other, like as some assume that the two wave documented field, small pi and capital pi, both have the ultralight mass Q. And we introduced the mixing interactions between them. Because the equation of the motions of these potentials are non-linear, so we assume that some simplifications with the bare mass term of the capital pi is the dominant compared with this mixing term. Then the solutions of the capital pi approximately follows the simple Fourier modulation. Then the recoupled equations, the nonlinear system can directly reduce in the linear equation, which is a form of the Mathieu type equation. The general solutions of this Mathieu type equation is the following. The solution is given by the multiplications of the exponential mu tilde, so-called Mathieu characteristic, and some periodic function. This Mathieu characteristic mu tilde is in general complex, and this will determine the dynamics of this system. And this mu tilde is a function of the parameter A and the Q of the equation. So over the parameters A and the Q, we can analyze our solutions with the mu tilde. The mu tilde has the real parts and the imaginary part. And we can distinguish the two regions. In the gray region, this is called the stable band. The real parts of this characteristic is the vanishes. So there's a no exponential growth behavior inside of this band. And this black region is called unstable band, which is the real part mu is positive. So in this region, so we can observe the exponential growth. And also we can classify the two regions for this unstable one more time. If the parameter Q is larger than the one, this is called the broad resonance region. In this region, the instability regions are wide, and the relative scale of the mu is also large. So the exponential growth is effectively sufficient. But in the left side of this acid one, which is the parameter Q is smaller than the one, this is a narrow resonance region. The instability bands are narrow, and this is characterized by some specific condition. When the parameter A is around the scale of the integer, only the disintermediate bands appear. So the first one is 1 and 4, and the next one appears in 9 and 24. And then the scale of the mu is relatively small, so the exponential growth is insufficient, and the amplification will be suppressed. Usually the broad resonance show that the parametric resonance behavior, which is adopted for the preheating after the inflation. This can provide amplified productions of the particle in the early universe. But in our system, the mixed wave documenters naturally lies in the narrow resonance regime, because this mixing term should be the subdominant compared to the bare mass term to avoid the radiations like behavior. So our system is in the narrow resonance regime. As a result, the amplification is insufficient. And also, if we solve the poor coupled equations with the non-linear plot, then there will be the back reaction, and this will make the terminations of the amplification. So our system will show that there's some slow modulation with the envelope behavior, and there's growth will be stopped at some moment. Such a slow varying amplitude can be analyzed by our solutions. The solution contains the exponential mu jet factor, and again the jet is defined like that. So that this near slow time scale can be obtained by the parameters, the real parameter view. So this slow time scale is roughly given by the 1 over the mu n with the 2 pi factor. And in the narrow resonance regime, this mu is extremely small, so this new time scale becomes naturally longer than the original wave documenter's period. So, for example, in this benchmark point, the original wave documenter's period is around a day, but modulations of the slow time scale is roughly the 1.9 years. And if we Fourier transformations of this wave envelope dark matters, then we can observe the side and the structures with the same spacing and the same height in the frequency space. So far, I only focused on the unstable region, but such a wave envelope dark matter behaviors also occurs inside of the stable region. In the unstable region, the non-vanishing mu's determine the slow time scale, but not in the stable region, the real part mu's are vanishes. So instead of the real part, the imaginary part mu is important for our dynamics. This imaginary part mu's are slightly deviated from the integer n around this n instability bound. So this small deviation delta eventually will determine the new time scale, as shown in this landmark point. And such a stable region analysis, we directly apply this to the dance imbalance of the galactic center with enhancement factors D for the initial amplitude. So as these increases, the factor Q is follows this red line. But after the D equal to 60, the material approximations are not varied, so there will be some irregular patterns in our dynamics, so we represent this as a density line. This is the theoretical comparison between the theoretical predictions based on the material masses and the numerical results of the slow time scale. The last curve represents the theoretical one, and the black curve for the numerical one. And over the ranges, the two the matches except the boundaries of the instability boundary, because at the boundary, the solutions have the circular-like form, so this makes some mismatches. And also, again, after the equal 60, due to the back reaction, the material approximations is invalid, so it's hard to define the envelope time scale. So such a mixed wave documenters can provide the interesting temporal behavior, like the wave envelope with the new slow time scale. This time scale can be analyzed by the material method. Such a non-harmonic modulation can directly affect the several factors if this document is coupled to the other particle, like as they can make modulations in the atomic cloud or lattice or other particular system. And in the remaining time, I will briefly talk about the implications in the between them. So if this document applies coupled to the heavy matter and neutrino, and this will generate the mass terms sort of over time, then this can make the modulations in the neutrino process, for example, the neutrino last over 30K. So this green curve represents the oscillation of the mass term, and when this mass term is smaller than the Dirac mass, then this will neutrino will go to the Cauchy direct type with the subfractions of this neutrino less than 30K. But if the wave dark matters, there are multiple wave dark matter views and they are mixing each other, then the temporal structures will be complicated. Now the oscillation amplitudes of the mass terms are also the modulation over time. So this will make the modulations of this tunnel, the subfractions of the neutrino less than 30K. So in some moment, this subfraction time will be long, but in another moment, the subfraction time will be shorter. So by the Fourier transformation, we can observe some multiple frequency peak, which can improve the sensitivities of the neutrino layer process. Also, this is another scenario. Also, the cosmic neutrino background, which is hard to detect, this can also get the modulations. If the neutrino sectors are affected by the wave dark matters, here we assume that the tachyonic bare mass term actively adapting some sociality through over time, and this can make the periodic symmetry breaking and restoration, and also this can make the modulation and the cosmic background. So in this talk, I talk about the ultra-lightweight documenters and possible mixing. They can be pseudo-non-trivial time-dependent structures like the wave envelope, and this low time scale can be analyzed with the parametric methods, and this can induce with modulation signaling the various sectors. Thank you for listening.
Okay, thank you very much. We have time for questions. There is a question.
My understanding, the argument of the form is that in the background field capital pi, in background field capital pi, the wavelength factor 4 pi can have a value phenomenal characteristic. But I just wonder how because I understand level, I see the capital pi heavier is tiny.
Oh yeah.
Capital pi can annihilate to the lighter, like
So yes, you're right. Is your concern is right. So the one thing I want to emphasize that is both the small pi and the capital pi can show that the wave envelope like behavior, and I didn't touch the benchmark on various detail here, but maybe it's still not here. So in our benchmark point, capital M and the small m is quite similar, only to 0.99% different. So there are no decay channel between them. Yeah.
I just wonder how can the pi have there are a lot of capital pi.
So that is just we assume that as in the condition as the capital pi is has a more fraction rather than the small pi. Yeah.
Similar question about two new Planck scalars. There are some common origin like Newman complex scalars. They are part of the model, or they are completely independent.
So they are completely independent. So there both the real colors here. So both the real color, and they are independent. Yeah, they are independent. Yeah, not like this.
And the second question is that you are considering only the zero mode, I mean the momentum zero mode.
Yeah, I don't understand momentum.
So there should be individual non-zero mode.
Yeah, so there are some leading order case of two.
Yeah.
Yeah.
So if you consider the non-zero mode happens, like green function.
Yes, I think that such a non-zero momentum will be important when we analyze the solid tunic some density profile or the some structured formation. But in here we only focus on the how this mixing term can modify the modulations pattern. So yes, also we should analyze with such a non-zero momentum for the structured formation over